But we got the garbage monster over here really banging around. They're really getting to it. Flipping them dumpsters. I always wanted my own dumpster. Alright, so any rational human's gonna say, Schindler, what the fuck does your old hot rod or hot rods and your old electric bikes have to do with making wires transmit data faster? What experience could you possibly have with wiring things and improving performance, or at least detecting what the limiting factors are on performance? So let's dig into that. So performance increases. Sometimes 10% is all you need. Sometimes 50% will make all the difference in the world. And sometimes you can grab 5,000% with constraints. In an internal combustion engine, we all understand that you mix air and fuel together. You ignite that at a certain time relative to where the pistons are. You get an explosion, the piston pushes down, right? So, well, what happens? Spray more fuel. Well, it just goes rich. You get less power. You have an air-fuel ratio range of like 9-to-1 to 17-to-1. Just goes pig rich. Okay, blow more air and spray more fuel. Oh, all right. So you can put a turbocharger driven off the exhaust fumes. You can put a turbocharger driven off belts. You can put a supercharger positive displacement. You can blow nitrous oxide. You can force air in there, mix it with fuel. Okay, how important is the fuel mixture? Well, that's why we got multi-port fuel injection, right? How important is the timing? Well, that's why we have coil over plug. You can make a bigger boom in the hole. Double your power, quadruple your power. This car right here is a 280 horsepower car. Guys lay down 1,000 horsepower dyno numbers all the time. What's the unintended consequence? Fuck, First, an engine is a very inefficient thing. You create a lot more heat. You have to have a better liquid cooling system. Engines are full of oil sloshing around, and it gets vaporized and splashed, and you need an oil catch can, so you're not, blowing that by. Oh, well, this particular engine comes with forged pistons and sufficient block, but in things like the Honda that I rebuilt, you need to sleeve your block and run special rings, special forged pistons to take all that force. You start beating up your rods, beating up the crankshaft, beating up your fucking all your bearings, right? You're gonna need the ability to control the timing of the spark, the fuel, the air. It's a really complicated endeavor, right? So I have personally supercharged Hondas to great expense, only to get 50% performance increase. Now that 50% means a lot when you step on that poop stick and that thing starts moving out. Oh, you feel it, it's there. But yeah, dollar for dollar, it's not a very good return. E-bikes. Oh, we disrupted the e-bike industry. An e-bike used to be 24 volts to 36 volts. It used to run 20 amps, all of them. They were all under a horsepower. They were all miserable. All right? So my first e-bike was 100 volts. That's 4 times, a 24 volt e-bike. So you're gonna get a 4x improvement in top speed if you don't consider velocity squared and velocity cubed, which you need more torque to get past. And we took the current limit from 20 amps to 40 amps to 60 amps to 80 amps. That's 4 times the torque. So we multiplied the available top speed by 4, we multiplied the available torque times 4, and power equals volts times amps, so you get 16x. All right, that's a 16x. What's that, 1,600%? So what's the unintended consequence? I don't know, started detonating fucking MOSFETs. Oh, what's the first thing to go? Well, if you just blindly increase the voltage, the first thing to go would be a few internal circuit components which couldn't handle it, like the voltage regulator. Easy enough fix, like one resistor. You had to change the programming a little bit because now your cutoffs were a little bit different. You had to solder the shunt in order to lower the current. All in, you're in for like $5 to get like a 16x improvement. And then of course, a much bigger battery. that's a much better chemistry that can push 100 amps. You know, we're not talking about two alarm panel batteries duct taped together, wired in series to make 24 volts with a 5 amp fucking continuous output and 10 or 20 amps peak. We're talking about packs of high rate 20C lithium with no label straight out of China, dude, that will fucking light your house on fire. I never lit my house on fire. I fundamentally understand the technology and I put it to work. So what was the big hang up? MOSFETs. Engineers somewhere understood that the heat in a MOSFET is the current running through it squared times the internal resistance. This wasn't widely enough spread. Manufacturers were swapping MOSFETs for the cheapest available. Some real penny-wise, pound-full of shit. Well, what would happen is they would underperform. They would blow up. And so they would just keep changing the shunt to lower the current until the and lowering the voltage until the devices would remain stable, and then they'd ship them because they'd already made 10,000 units and they didn't want to throw them away. And these would hit the US shores, and then we would then unfuck them, unsolder all those MOSFETs, and solder new MOSFETs in. It turns out that the e-bike controllers didn't need better heat sinking. They didn't need higher voltage components. They didn't need to be bigger. They did need to be more expensive. So the MOSFETs they were being populated with were about 10 cents each, and the MOSFETs we were populating them with were about $5 each. To tell someone producing in China that they need to swap from a 10 cent part to a $5 part was too much for them to fucking swallow. We started shipping parts over there and saying, build with these parts. You saw a revolution happen. Now, we were working out in the lunatic fringe. 100 volts with a 100 amp current limit, lunatic fringe, dude. But you'll see that we, me and many others, proved that there's margin around that you can get that working reliably. So if you cut it in half and say, how about 50 volts? And you cut it in half and say, how about 40 amps? Well, now the standard is 50 volts and 40 amps, dude. That's actually quite a bit of power. A couple thousand watts, dude. Couple horsepower. A couple horsepower is a fuck ton more than a half horsepower. You know, big, like over 4x improvements. And what does it boil down to? Well, fundamentally understanding what the failure mode is. Ohm's law, V equals I times R. Power, V equals I times R. V equals I times I. All right? There's power output, and then there's inefficiency. The inefficiency of the controller, part of that was the current squared times the internal resistance. That's the heating inside the MOSFETs. There is continuous, burst, and peak. The instantaneous power at T0 inside the MOSFETs was so high that they were boiling their own fucking intestines, churning from a solid to a liquid to a gas and exploding because the internal resistance was too high. These were all counterfeit MOSFETs that didn't even really hold the high voltage standard. You know, like they might claim to be a 60 volt MOSFET. They were like a 45 volt MOSFET. They were like factory rejects. So that was one problem. But the real problem is that they just didn't have their process worked out for the various layers inside. It was all wrapped up in patents and not shared, and all those expired. People started copying it. You saw Internal Rectifier lose the market, dude. You saw them get bought out by Infineon. You saw everybody start making low internal resistance MOSFETs. And we're talking about big differences here, like 400 milliohms down to 40 milliohms, down to 4 milliohms, now down to like fucking sub-million. All right? That eliminates the failure mode. Now, as the current flows, you can square it and multiply it times that internal resistance and end up with a power that doesn't melt the internals and doesn't cause it to detonate. This is what allowed us to get 16x performance improvements, being total fucking noobs to the industry. And this is what helped enable the fucking electric revolution, where you see everybody everywhere, if they want to, can have an e-bike that they can jump on and pedal and keep up at like 20 miles per hour and go straight uphill at 20 miles per hour and get reliability. Now, there's a bunch of other stuff in there that the industry added in, like the good ingress protection so that you can leave your back out in the rain. Good quality process so the battery packs don't catch on fire. All right. So those are 2 examples of performance modding to go faster, to get more torque, to produce more power. Is it more complicated to get more speed? No. Are there unintended consequences? Yes. Does it cost more money? Of course. So if we start out with the argument of, I would like to get more speed, but I don't want to spend any money, that's a non-starter. It can be done. It just takes like a major paradigm shift. You have to basically do something totally different. It means you have to change all the so in any kind of communication, you got a black box, a wire, and a black box. You can change the black box, you can change the wire, you can change both, you can change neither. There are 4 cases. If you change neither, nothing's going to happen. If you change both, you have to incur the cost of the wiring upgrade and the black box upgrade. So that leaves you with, can I change the wire? Can I change the box? Well, of course, you could change the box and use the wires differently. So the way that modern shit goes fast, like Ethernet, all they're doing, dude, is laying down a cable and saying, can I run a megahertz from end to end with you know, square edges? Can I run 10 megahertz, 100 megahertz, a gigahertz, 10 gigahertz? And so what defines that? Well, quality of the cable, right? You got Cat 5 cable, you got Cat 6 cable, you got Cat 7, 8, 9. Who the fuck knows? Who the fuck cares? If you just cut that cable in half and look at the cross-sectional area, what are you going to find? You're going to find higher and higher precision. Twisting of the wires, which is controlled. Shielding channel to channel, probably, which is controlled. Over shielding. You're going to find lots of shielding, lots of twisting, lots of consistency. Consistency. Shorter it is, the better it is. Longer it is, the more that you lose. Right? It's like real fun. It's not rocket science. So you can in serial do it that way, or you can go parallel. And this is what you see, like, you know, I've done a bunch of parallel processing. What do you see down on the motherboard? Well, you see parallel channels, right? You see parallel channels. So you get something running at a megahertz, we'll put 10 of them down. All right, you know, now we're at 10 megahertz. Then you have to mux and demux the data on either end. It's standards, it's precision, it's paralleling. Well, then how is it that Ethernet gets like fucking 50,000 times faster all of a sudden? And so many things are left behind. Orders and orders and orders and orders of magnitude back. Well, if you took an old Ethernet building from the 80s and you put all new shit in there, 10 gigabit switches, it's not going to fucking perform, right? Like you might be able to get it to, but then when the HVAC turns on, it's going to slow down, right? Like unshielded, poorly controlled, funky cables that are not qualified or not, you know. So there's 2 basic things that make a cable go fast. One is how well it works as an antenna, and 2, how well it works as an antenna. That's right, same thing. One antenna is the antenna that picks up outside noise, and one antenna is the antenna that transmits the desired signal. You have to minimize the picking up of outside noise and maximize the transference of the desired carrier frequency, and your data rate is directly proportional to your carrier frequency. You obviously can't carry, you know, a gigahertz worth of information if you can only transmit 100 megahertz waveform, right? And so you can get into funny business where they're sending multiple frequencies all next to each other, and that all works out to how awesome the hardware is. The fucking hardware is phenomenal, dude. Like, you're not gonna get a totem pole or H-bridge to fucking perform like super advanced routers and switches and, you know, Ethernet enabled devices, dude. There's magic in the chips, wicked magic. And I'm the kind of guy who cross-pollinates, you know, like if you need a real fast triggering system, I'll use something different. I'll go grab a high-speed CAN chip, you know. I know that will work to it if it's managed correctly. Will work to a reliable megabit. So let's talk about CAN. How did I first become introduced to it? I spent a bunch of time with RS-422 and RS-485 and GPIB and USB and serial and even parallel, talking with test equipment. Usually in a pretty controlled environment, usually against pretty good stuff. Didn't have a lot of noise problems. I became introduced to applications where we had to work in a configuration that couldn't be changed. It's been long enough now, I can just tell you, that's a battery box. There's high voltages present, hazardous, deadly voltages. There's flashpoint dangers, like if you drop a wrench, it will literally detonate and explode. Like I've taken a lot of explosives training. The kind of explosives you'll work with when you're doing basic assembly and stuff like that, you know, it's like the size of a marble, you know? But if it's right, if you squeeze that marble in your hand's going to turn into vapor. I've watched many videos of gloves full of steak turning into vapor, all right? If that marble is a meter from your face, you're going to get fucking puckered, dude. You're going to be getting shrapnel, right? And if that marble is 10 meters away instead of a blast box, you won't even hear it. So there's this concept of diminishing returns as you get farther. Like, you know how magnetism works? You know, if you're right on it, it's extremely strong, and then you get an exponential roll off as you pull away. That's the way explosives are, and that's the way noise is. So I got a little bit off track there. The defining difference that drove change in the way we used CAN was the need to perform an OTA. Traditionally, you would always just grab your JTAG. We use JTAG programmer, right? And you would fucking tear open the assembly, and you would plug in the USB to your computer, and you would plug in the 10-pin connector, and you would reflash firmware. Most people didn't even use bootloaders back then. You just literally pushed your firmware right onto the unit, right? Well, something like a high voltage battery, it has all of them are the same, dude. You have a main board, and we're not talking about any specific manufacturer. We could be talking about Ford Think right now, which is extinct. We could be talking about Tesla. We could be talking about any of them. There's some kind of motherboard which interfaces with the rest of the car. It has communication channels on one side that are appropriate for the automobile environment. The other side of it, it talks with a high voltage battery, and they all do it a little bit different. It's all isolated, and everybody's got a novel way to do it. Linear technology came up with a way, and TI came up with a way. There's all kinds of different ways, and the industry is now settled. At one point in time, it wasn't. Well, you might have 15 boards inside of a high voltage battery, and each one of those is on a module. And then you might have the main board, and it is not feasible. And we've been doing this lately with an old Ford Think. A friend of mine is he really goes for it. He picking up these old broken Ford Thinks, and he fucking drops the battery out of the bottom, and he peels the fucking lid off, and he goes into all these different super high voltage, super scary modules and tears them down and gets the fucking, you have slave modules and a master module. I know it's not popular these days to use master slave configuration, but that's what it was called, and that's what it is. There is a master board and slaves. So there's different terminology that is used now that isn't as clear. So once more clear terminology comes up, it's not client server, dude. In that kind of bus, there's a controller, there's a master, and then there's what they call slaves. So sorry, but that's the terminology that is used in the reference manuals. So you can change the firmware quite readily in the master board. And in this particular application, there's actually a flap you can pull off and actually get to that board. You can plug in a JTAG program, or you can change the firmware. And I don't know whether they were using bootloaders yet or not. Presume they weren't, because we still have to JTAG program them, and they can't take an OTA. OTA is over-the-air update. That's when you have a medium like Ethernet or CAN or RS-45 or SPI or RS-422 or anything, or USB or serial or UART or anything, I2C, and you send a fresh bag of code to the unit because it has a bootloader, and that code runs on top of the bootloader. Remember, I majored in compilers. Yes, I understand microcontrollers. I own about 700 microcontrollers. I can write firmware for anything. I've written a lot of software. I've written a lot of mobile app software. I've written a lot of web software. I fucking get it, dude. I'm not a big GitHub guy, but I certainly know how to push some code out down the pipe. I've pushed a lot of code down the pipe. If you were to add up all the code I've pushed down the pipe across all the machines I have in the industry, hundreds of millions, billions, hundreds of millions of fucking bin files and hex files I've pushed down the pipe. So I understand it. Now, the Ford Think, which we'll pick on because they're out of business and there can't be any confusion about intellectual property, which is the root fucking cause of all problems in engineering. People trying to make money and keep things secret, and then fucking having to work together and still trying to keep things secret. All right, they use CAN, and in another application, which I won't specifically identify, they use CAN as well. And there's like old school slow speed CAN, and there's high speed CAN. All right, if you use old school fucking CAN, dude, it's like a half an hour to do an update, and it usually crashes because they would do the CRC at the very, very end. So you might wait a half an hour, and if you had a single bit error, the whole transmission was lost. Old timers from the industry remember these days. Since then, modern code performs checks on a piece part method. You might break something up into 1,000 pieces or 10,000 pieces. Error check those individually and do retries on individual pieces. It's just like 100 more lines of code. It's not that complicated. It's just in the early days, there was very early code flying around where no one had really taken the time to get in there and make it better because it didn't recognize the perils of the physical layer. The perils of the physical layer are that it's an extremely noisy environment. The modern EV is extremely noisy. You had to convert the brake booster. There's no source of vacuum anymore. You had to create that. You had to convert that over to pump. You had to make all of the water pumps electric. You had to make the windshield wipers electric. You had to make the fucking heater electric. You had to make the AC electric. You have infinitely more communications and wires running everywhere. Oh yeah, and by the way, there's gigantic motors and gigantic batteries that are fucking ringing like a bitch. So it's a noisy environment. Not such a friendly environment for sending over-the-air updates over fucking CAN, right? So I don't remember which years, like things come into use before they are officially documented. Sometimes things are documented, they never come into use. Like the guys who sit around the table at the old fucking standards lab officially release some new standard. It's usually just for the fucking government or just for the military or just for aerospace. People who want to use it in an airplane or in a medical device or something like that. Realistically, shit is being used everywhere, and the standards come from that use. Because someone decides to write it up so that they can make it official, fucking rubber stamp it with ISO 9001 or whatever. We are in conformance. Or it's when different industries collide and they have to communicate, and one can do it and one can't. So here we are talking over this CAN bus, and you have low-speed CAN and high-speed CAN. At a certain point, you'll see there's different standards. There is a standard for high-speed CAN. It is extremely strict. It offers you a trunk that can be very long, but it offers you node drops that are limited to like 8 inches. Yeah, you can make it 32 inches, but you won't be to spec. and you won't have guaranteed performance. If you want the guaranteed performance that is robust to noise, that is reliable, that is consistent, that doesn't get bit errors, that doesn't have retries, then you had to make a trunk that was of an arbitrary length. And we're using a far shorter trunk than you would ever find in a factory. And you needed to have nodes that were very short. And so this was solved by routing the trunk all the way around the battery, from unit to unit to unit in a daisy chain configuration. In order to not have a ground loop nightmare, it's all isolated. So the grounding does not go into ground loops. And all the grounds are staggered. It's a perfect fucking storm. The first ground's at 0 volts. The second ground's at 50 volts. The third ground's at 100 volts. The fourth ground's at 150 volts. The fifth ground's at 200 volts. Onward up to 400, 500, 600, 700 volts. So I know a little bit about my fucking ground not being true and correct, right? So that's why you start seeing standards that involve isolated drivers. It's in order to manage a grounding system where you can't have ground loops. Ground loops fuck you up super bad. They tightly prescribe the twisting. There's an actual certified cable you can buy that is twisted just to the right amount. And they strongly advise the use of shielding, and they describe how you drain those shields. So getting back to, there's two kinds of antennas in high-speed communication. One is an antenna that collects noise, and one is an antenna that transmits desired data. You minimize the noise collected and you maximize the data transferred. How do you do that? Well, differential. By twisting the wires, you make them see common noise. So whatever noise is present, it's on both. You then have hardware that does a mathematical, in-circuit, real-time, coprocessor type subtraction of what is on both wires. That subtracts the noise from the signal. You improve the signal-to-noise ratio, and you get good data. Alright? That's one way to minimize the way a cable acts as an antenna to collect noise. You literally collect the noise, and then you subtract it. Sometimes the noise is too big for that. That's when they prescribe a shield over the cable. The noise hits that shield and literally drains off to a potential, to a ground, which is related to that noise. So noise, sometimes comes from fucking nowhere. But usually, the noise comes from someone close by. And there is some kind of fucking path back. There is some kind of chassis. There is some kind of shared ground. There's something, dude. And so if you simply drag that ground over your cable and you don't touch it, that noise will fire into itself and loop back. You're short-circuiting the noise past your antenna. If you put an antenna on the roof of your house and you pick up channel 11 and it's a little bit fuzzy, that's great. You can watch channel 11. If you then go up there and start putting metal boxes around your antenna, you can no longer get the same fucking signal strength, right? You might not see it at all. That's shielding, right? So there's intended shielding and unintended shielding. So in order to achieve high-speed CAN in high-noise environments, we use two methods. One is making the noise common and subtracting it out at the hardware level. You can read 300-page data sheets until the end of time. They all do it exactly the same. Two, we add shields in an attempt to make the communication wires less of an antenna to noise. Shielding and twisted pair. Fundamental, more understood than anything else, anywhere, at any time. Now, that's the easy part. What's the hard part? Well, how do you make it a better antenna to radiate the signal you want? Oh, well, LTE or Wi-Fi or Bluetooth or BLE or 900 megahertz or fucking Citizens Band anything, they're firing through the air, right? Well, the air is the medium. So if you put a mountain between us, it doesn't work good. If you put a building between us, it doesn't work good. If you go in the basement, it doesn't work good. So think of communicating over cables as actually radio frequency. I know, specifically it might not be. Think of it that way. It is not, ooh, look at that pack of birds. It's a flock. It is not a traditional, say, H bridge banging up and down. I forgot my insure. God damn it. Well, at least I have a bagel. I'm going to start eating my bagel. It is not a traditional open collector or H bridge or anything like that, dude. It's actually radiating high frequency, and it's carrier frequency. So if you've studied your RF and you know how data is put onto a carrier signal, on and off and pulled off, and you understand like bandwidth and all that, it makes perfect sense. So what I did, I'm going to talk with my mouth full, is they just took radio technology and put it on a medium of copper instead of a medium of air, because air is problematic. Alright, so what's the problem with that? It's an imperfect medium. Not because of the amalgamation of the copper, because it has impedance in the form of ohms resistance. It has impedance in two more fucking vectors. There's capacitance in those lines, and there's inductance in those lines. They're not fucking simple linear DC things, right? If you run a sweep through the cables from 0 hertz to a gigahertz, you're going to find certain points where your impedance is high and certain points where your impedance is low. Characteristic impedance, right? Like, literally, there's inline inductance in the cable, and there is parasitic capacitance across it, and you can describe it all in those fundamental understandings and prove it by running a frequency sweep and change the physical characteristics of your cable until you get a low impedance at the desired frequency. If you want to go faster, the desired frequency is higher. Alright. What the fuck is terminating about? Well, have you ever bounced a frequency off of something? Have you ever experienced skip and had your Citizens Band radio all of a sudden get 50 miles range instead of 5 miles range? Have you ever heard sound echo off a wall? Have you ever gone to the... Whoa, someone flicked a cigarette out the window. Have you ever gone to the Exploratorium and sat there with the dish behind you and heard someone all the way across the room whispering because it acted like a radar dish and captured that and focused it in your ears? Have you ever heard an echo in the High Sierra as you yelled into a big chasm? Right? Reflections. Fucking shit bounces. Oh boy. Right? So, it turns out that some geniuses figured out that if they make just the right echo chamber, you don't get echoes. Think of this like when you go to the testing lab, you're going to test your device. Have you ever been in one of these big rooms? It's a room that might be the size of a bedroom, and it might be the size of a football field. And the walls are covered in giant fucking spikes. They might be 10 inches long, and they might be 10 feet long. What those do is they minimize reflection of signals. That's a physical way to do it. It turns out, if you stick a 120 ohm resistor on either end of a CAN bus, you squelch out reflections. So in terms of like major, minor, you know, you might have a major carrier at like however many dB, and then when it reflects, it's obviously reduced in amplitude, presumably. That shit gets squelched out, gets filtered. you improve your signal to noise ratio. Now, that's way down the path. After you solved a bunch of other shit. So the other resistors you see are just what we talked about the other day, which is low power design drives open floaty circuits. And open floaty circuits are sensitive antennas. So hanging pull down or pull up resistors off of them causes them to not be floaty. Floaty things are good antennas. Noise doesn't like to do work. Noise is lazy. If you attach pull-down resistors, you hold things in a known state, and you don't get bit flutter. Bit flutter is that analogy I gave you the other day of somebody fucking yelling outside your bedroom window. That's bit flutter. If someone yells outside your bedroom window in the middle of the night, you gotta get out of bed. You gotta lift the drapes and look out. You gotta walk out on the porch, right? Well, imagine if they yelled every 3 minutes. Wears you out. Fucks up the protocol. So, you oftentimes find that there's high power, high reliability, and low power, low reliability. Just like with e-bikes or cars, in order to achieve, there's, better, faster, cheaper. Pick two. Pick one. In order to achieve power efficiency, they gave up margin. So, if they're not talking on the bus, they go floaty. Because they had a driver to operate for. They have a requirement to operate for under 50 milliamps, or under 5 milliamps, or under 500 microamps. So they achieve that by making floaty chips that don't actively pull on the lines. So if everybody goes low power, the lines start flying all over the place. You'll find all kinds of Tom hackery. People might add a little tiny bit of capacitance to a line. I'm talking like a picofarad, like a scope probe. Sidebar: attaching an oscilloscope or logic analyzer to a signal grotesquely changes the behavior of that signal. There's like a scientific experiment that describes it. But just the 10 puff or 20 puff of your scope has a huge impact on the behavior and performance of the circuit. So that's why you buy $10,000 oscilloscopes. They have less intrusive probes that allow you to see things for what they are. So the way people work around cheap stuff back in the day is they just put the 10 puff in the circuit, and then when they want to measure it with the scope, they take the 10 puffs out, the 10 puff cap out, and they put their scope probe in there. And it turns out when they validate that with a higher performance piece of equipment, they're getting a true read. So if you want to speed something up, whether it's a car or an e-bike or some data lines, you first have to fundamentally understand the failure modes of it. Why is it not going as fast as you want? And you have to understand the unintended consequences of performance increase. What will happen if I increase its performance? What do I have to give up? You're going to have to give up something. Maybe you have to give up power. Maybe you have to give up cost of wiring. Maybe you have to give up cost of electronics. Maybe it turns out to be a wash and you want to go a different path. Because there's bounds to anything, there's diminishing returns. Like, if you go after a UART wire, which has been done, I'll choose this because it's been done 1,000 times in the industry. Do you know how many times someone's tried to drag a UART wire out of a unit? Ground, power, RXTX. Never intended to go more than an inch or two. Never intended to go over 115.2. Well, you'll find in all the modern chips that chips and peripherals that a lot of things actually communicate using UART, and they do it with like a 1 centimeter long trace on the PCB. And in the modern chips, they now run software controlled DIOs, and so every chip has a multiplexer on it, and every chip can, has like a little 8-byte buffer and all the things you need to do UART. So someone figured out how to Tom Hackery UART over 115.2 up into the quarter megabit, to the half megabit, to a megabit. UART at a megabit. It's very real. You can do it. The kind of thing you see on when a CAN chip or a RS-485 chip or an RS-422 chip or some kind of special A to D chip interfaces with the MCU. Maybe it's SPI, maybe it's I2C, maybe it's UART. Very rarely is it parallel. Right? How do you think these signals get into the microprocessor? And how do you think they hit numbers like a megabit? Well, they're using a chip that can fucking toggle its ports at 20 megabits. So it doesn't have any trouble toggling its ports cleanly at a megabit. And it just so happens that it's called a UART. That's not what they're doing. Now, someone sees that and they're like, fuck, dude, you can do a megabit on UART. And you can. In modern Arduino, you can buy an Arduino for $20 from Adafruit or SparkFun, flop it down on the table, buy a chip, throw it on a proto board, attach them together with very short leads, and you can see megabit performance. Now, if you try to separate those out into next assemblies, like a foot or two away with a cable, you won't even come close to it. You'd be lucky to hit 115.2. And nearly all USB to serial cables on the market can barely hit 115.2. And if you start extending those USB cables, fuck, dude. Major data rate. And by the way, that's the way USB-C works and all those other things. They just put more buses in parallel. Here we are pulling up on Fremont. That's how you approach performance modifications to legacy equipment. I've done it with cars. I've done it with e-bikes. I've done it with Arduinos. You have to fundamentally understand the failure mode, fundamentally understand the unintended consequences, choose better, faster, cheaper, pick two, and you choose faster and better. And so that means you'll lose cheaper. And in the better, faster, cheaper is the amount of power it draws, the complexity of the circuits, the expense of the cables. And then you can sit down and you can make a proof, unconditional proof on the bench. And then you have to make a representative bench test. And so, you go out to take a random sampling, try it in different spots that are known configuration. And you'll find the limitations very quickly. Scientific method.